Yes. Hello, this is Wilhelm Kirchgers now from the Paderborn University, Germany. You can hear me?
Yes.
Right. Let me share my screen. Okay. So thank you first for organizing this competition. We really had a lot of fun working on that problem, and we appreciate your effort and your focus on the community and the open source thought here. I think that will be really great in the end. So to our solution, first to us, maybe we are 3 PhD students, 1 undergrad student and 1 supervisor. And when we started working on this project, the first thing we did was to dive into the data. Can you see my slides actually?
Yes.
Okay. So first of all, we had a look at the data. That means we were plotting a lot of distributions, scatter plots, we were looking at the different variables, how they could be explained by other variables. We were looking at the pH curves, of course, and how we could classify the different waveforms best. And after we had a general idea what we have to deal with in this competition, then we would just start with modeling, actually. And in this data set, you probably know we had 1 degree of freedom, what we would actually like to model. It was either the scalar power loss or the H field. And we agreed that modeling the H field might be more promising or more interesting because there's first more information that we could infer from. The models that would predict the H field would be also more interpretable and maybe also more useful in a design phase. And if you want to model time series or sequences, you could use MLPs, multi-layer perceptrons, but more appropriate would be some recurrent structure or convolutional neural networks. And early on, we were agreeing to use one-dimensional CNNs, one-dimensional convolutional neural networks with circular padding, because it seemed not necessary to resort to a recurrent structure since we had the full sequence available all the time. So we could look into the future, we could look into the past. It's all available. We don't need to do some causal prediction. So using symmetric kernels in a convolutional neural network seemed very likely to be successful. So 1D CNNs were the way to go, or the model to go for time series estimation. But another important phase in our solution was the normalization as well. So here you can see the pH curves, or a certain subset of the samples for all materials before normalization. So in different colors, you see different pH curves. And you can already see that there are some pH curves, they are much smaller than the other pH curves because there's more power loss in that excitation. And we figured that for a statistical model, it would be probably nicer if all those polygons, if we want to call them so, would be of a uniform shape or more similar to each other. So we had to think of a way how to normalize them in such a way that the learning task is a bit more smooth. And what we came up with was the following. So the B field is a very simple normalization. We would just divide by the maximum absolute B value that appears in that specific trajectory, in that specific period. So that is a pair profile normalization of the B field at the input side. And at the output side, we would not try to estimate the H value or a globally normalized H value, but that would be also pair profile normalized. That means, in particular, we would divide each H value first by a material constant, H lim, which is the maximum absolute H value appearing in the entire material-specific data set. So you can understand that as a material-specific constant. Same with B lim, which is the maximum absolute B value appearing in that material-specific data set. And we would also divide by, again, the maximum B appearing in that certain profile. So that means we would also have a target value, which is per profile normalized. And you can see the result of that normalization here at the bottom, where you can see that all those polygons, all those BH curves, they are more unified. So this was actually a very important step. You can see a comparison here. We see here the worst case predictions of our H field predicting CNN model on material 3F4 on the left side with a global normalization of H, so no per profile normalization. And you can see the worst case estimation here for these profiles. By bare eye, they look pretty okay-ish, but the error on the power loss was up to 257%, which was way too high. And after we used the per profile normalization as a target and then denormalizing later after the model is trained, the worst case error of the power loss was decreased dramatically to 46%. And I think if a lot of other teams would also try this normalization in case they have a H field predicting model, that is probably something they should try out, and probably they would also see very much improved performances then. So much to the normalization. We also did some feature engineering because we think that is often more important than tuning hyperparameters in a model. So we had a bunch of time series features and a bunch of scalar features. And for the time series features, important features were the first and the second derivative of the B value of the signal form. And those are also, again, physically interpretable, because especially at those points at the second derivative, those are also good proxies for the switching transients. So the H field would also show spikes in the signal form if you plot that over time, which is a good hint for the model that probably there would be a spike to model. So you can see all the time series features and scalar features here in our table. It's not too many because we had to stay concise, right? If you have too many features, then you would also have, again, more parameters. So we try to distill that to the most important ones. For the scalar features, you can see here on the right side, it is just a bunch of variations or aggregations of the B field, like the peak-to-peak value, the logarithm of that value, the mean absolute first derivative, the logarithm of that again, and the waveform was one hot encoded. OHE stands for one hot encoded. So that gave us then all the features that we needed for the solution. So you might ask yourself, how do you come to the power loss prediction if you are estimating the H field? And what we used here was the so-called shoelace formula, which is a very old formula for how to calculate the area in a polygon. And since B is given and H is predicted, with that formula, we could go ahead and calculate what the predicted power loss should be then. So this is a simple formula here. However, and this is probably also very interesting, during our first data analysis, we figured out that even if you had a perfect H estimator, you wouldn't get perfect power loss estimations with that shoelace formula. Here you see what errors you would get if you had a perfect H estimation and use that together with the shoelace formula for a power loss prediction. And you see that the errors, the relative error, it could go up to 8 or 9%, which basically means that if you would only predict the H field, you could put a ton of effort into this modeling task, and in the end, you could never be better than up to 8 or 9% here, which was very problematic. So we also put a lot of thought on how to solve this or how to overcome this discrepancy. And the solution to that was to merge the two learning problems into one. So we would not only learn to estimate the H field very precisely, but at the same time, we try to estimate the power loss as well. So we would have two target values. So that is probably a good time to show the architecture. It looks like this on a very high concept. It looks maybe a little bit complicated. So let's decompile that from the bottom up. So you can see so generally on the left side, you can see our branch for estimating the H field. And on the right side, we have here a branch for correcting the power loss estimate. And here on the left side, we have time series features here at the bottom. And here on the right side, we have the scalar features. For the time series features, we used for the last 5 materials, we used all the 1024 samples. And if we apply 1D CNNs here on these time series features, for each next subsequent layer, we would also have a feature space again of length 1024, so that in the end, in the last layer, we would end up again with a prediction that is 1024 samples long. One interesting challenge was how we could merge time series features together with scalar features. And we solved that by first projecting the time series features with a 1D CNN into the first layer. And the scalar features are projected into a first hidden layer by a MLP. And this activation of that MLP would then be just plainly added on that first activation of the 1D CNNs, so that the activations of the MLP are basically a bias that you put on a certain subset of all the neurons in that first CNN layer. So by having the scalar features projected into a feature space and then added as a bias, we had both information already at this level here, both the time series features and the scalar features. Yeah, and from here, we would transform that again for 2 more layers, 1D CNN layers, until we have only one time series. But this one would not represent the H field yet. We would also add a residual connection, which you can see here on the left, where we would add the normalized B value onto this activation here at the top. And what this means basically is that the model only needs to learn the difference between HN and BN. So if there's almost no power loss, then the model actually doesn't need to learn anything. It would almost predict already the perfect H field because the B field is given. So the model only needs to learn the differences between BN and HN through that residual connection. So, and it doesn't stop there. We also apply then a mathematical operation here, which is just subtracting the mean along this predicted feature space, because we know physically that the H field should be bias-free. So there's that subtraction then. And that will lead us then to the actual estimated H value. And that was the situation for us up until when the pre-tests were due. And after the pre-tests, we came up with that right branch here, where we would also try to correct for the power losses. And this branch is a bit more simpler. Here we would just have a MLP with 3 hidden layers that would only act on the scalar features. And the output is not directly the power loss, but just a correction term between minus 10% and plus 10%, which we would use to scale the calculated area in that polygon to account for the power losses that were inexplicable by the H field estimation. Okay, so we have that shoelace formula here at the top, or the polygon area calculation. And that one is a bit modified such that we can scale that area again a little bit, which is learned from scalar features and through a MLP. So since we have two learning tasks, we also need two cost functions. And the two cost functions that we used were first for the H field, just the plain mean squared error. And for the power loss, the competition was using the relative error. But if you use the relative error for training a model, you would dramatically overemphasize those samples with a low absolute power loss, because the absolute power loss would be in the denominator. And in order to have the model learn each sample equally well, we searched in the literature and we found that actually the mean squared logarithmic error would be a better cost function for such cases. And it fitted pretty well because we were targeting the logarithm of the power loss anyway, because that would be a more Gaussian distribution. If you look at the distribution of the power, the logarithm of that, it looks more Gaussian, and that is more appropriate for machine learning tasks anyway. So that's why we stick with the MSLE then here for the power loss. One problem arises though, because the power loss prediction depends on the H field estimate through that shoelace formula. So we had to weigh those two cost functions between each other, and we came up with this moving average formula for that. And we have that weighting term alpha here for the total loss, and that would scale linearly those two cost functions between each other. But we haven't had a alpha to be constant, but we rather scheduled it. You see the scheduling here at the very bottom. So alpha on the left-hand side, and on the right-hand side, beta is just equal 1. So you can actually ignore for now this parameter. Beta is just equal 1. In the beginning, alpha would be almost 0, because I epoch is the epoch in which we are currently training. So in the beginning, alpha is almost 0. So we would almost ignore the loss on the power loss prediction and put all the weight on the loss for the H field estimate. And then gradually, the longer we train, the more weight we would put on the power loss estimate, and less on the H field estimate, such that in the last epoch, we would only look on the power loss estimate and not at the H field estimate at all anymore. And if we look at a learn curve as an example, it looks like this. We can see here the training loss for H, the training loss for P, for the power loss, and also the validation loss for H and for P. And you can see in the beginning, both cost functions reduce almost equally. Although we only look at the H field estimate, the power loss also improves, because the power loss somehow depends on the H field estimate through that shoelace formula. But at some point, since the weighting is gradually changing to the power loss estimate, we can see that our H field estimate actually worsens for the sake of a better power loss estimation. So maybe this is an interesting finding, and yeah, it's not so satisfactory, of course. We would actually like to have both quantities equally estimated well. But since this competition is about the best power loss estimate, we made this decision that we are willing to sacrifice H field accuracy for the sake of a better power loss estimate. But maybe in the future we can come up with some construct that would have both values equally modeled. Okay, so this was the architecture so far. How did we come up with our hyperparameters then? So you can see here on the top left a small hyperparameter study where we were varying the amount of neurons in each layer to see whether we can get a better performance if we have more model parameters. And you can see here that we went between roughly 1,000 parameters up to 10,000 parameters. And except for the first step from 1,100 parameters to 1,700 parameters, there's almost no change in the accuracy, only a slight one for more parameters. But the biggest gap is here for this first change in parameters. And the reason why this one is so high is because between the first two parameter variations or model variations, we would erase a complete layer in the CNN. So that would be a very dramatic change in the topology. And for the other topologies or other models that we can see here, where we don't have a big change, there the amount of layers would stay the same, but we only would vary a little bit with the amount of neurons in each layer. Yeah, and since we wanted to have the highest estimation accuracy at the lowest model size, we went for the Pareto front and choose the model at 1,755 parameters as our final submission. You can see here at the bottom right an example prediction of such a model to get an idea how that would estimate. It also means if we are in a design phase later where model size is not so important, we could still gain a bit more accuracy by varying the hyperparameters a little bit. Okay, and last slide. What did not work? So in the very beginning, we also jumped on the neural ordinary differential equations, but there was two major challenges in implementing them. So first of all, there is no really precise differential equation in the literature, which we could leverage here. We could only use a very general differential equation, which wouldn't lead us anywhere. And the question for the initial value was not easy to answer. So that's not only for nodes, for neural ordinary differential equations relevant, but also for any recurrent structure. If you use a recurrent neural network for H-field estimate, at some point you need to start. And if you initialize with some random number, your model needs a little bit of time to recover from that wrongful initial value, right? So how would you correct for that? That was not easy to answer, and in the end, we thought it's not worth it because we have the full trajectory anyway, and we could just use 1D CNNs that are symmetric in time, so they use a few samples in the past and a few samples in the future to come up with one estimate for the current time point. So that also means that all the data augmentation strategies where you would change the shift of the phase or change the phase or do some other variations in that regard, they are not necessary anymore because it makes no difference for a 1D CNN. We also had a look at gradient boosting machines or XGBoost in this regard, but in the end, it had way too many parameters. And the accuracy was not in the same way better, so it would lose against the CNN approach. And what also did not work was FFT features. We used FFT features to better classify the waveforms. For that, it was helpful, but for the model, it made no difference, or the accuracy would actually worsen. All right, and that's it from our side, and I'm looking forward to your questions.
Yeah, thank you, Wilhelm, for both the wonderful work and the excellent presentation. It's really high quality thoughts, and I have to applaud your guys' work because I think your model performed well across all the 5 materials. Like they are all top performances, and also you are doing the edge loop prediction, which naturally make the size a little bit bigger. But I would say, like you said, in a real world scenario, predicting edge is more useful and more general. And that's why if you choose the path of only go with the core loss, maybe you can compress the model size a little bit even more. But even that, your model is not that big. It's still very small compared to in a full rank. So regarding it's very good to point out the mismatch between B and power, the edge and power, and that may come from the way we get the core loss, because we didn't use any other method to get the core loss. It's just based on B and edge. And Haran may clarify. So I don't exactly know what algorithms we use. We also adopt one algorithm to calculate the area. So maybe the difference just comes from the way you calculate the BH area and the way we calculate our BH area. And it's an interesting question. What's the most rigorous way of getting core loss from the time domain information? Because what do we measure? The raw data are B and edge. So I would say edge is more true to the physical world. But in the end, in practical design, we care about loss. Haran, do you have any comments on the BH loop and loss? And Shukai, maybe you guys know more about what we do.
Yeah, I think how we calculate the core loss from the BH loop is just by a numerical integral, and I think it's quite similar in terms of the expression with the equation that the team is using, I think.
Right, but there's difference, like up to 8% difference. That's quite significant, right?
So,
yeah, that's probably for those samples where we have a very low absolute power loss to begin with, and because it's in the denominator. Yes. I think then we get to that 8% pretty easily due to numerical errors.
That's right. Yes.
Yeah, exactly.
Yeah, go ahead.
Yeah, especially when we do because in the challenge we provide the data in the 124 like single cycle data, and by doing that, so essentially you have 124 data points in each of the cycle, which means for the numerical integral, how you do it, like you do forward or backward, it could lead to quite a difference, I guess.
Right. And just one more thing, I really like your reasoning behind 1D CNN. So this is basically 1D CNN give you time domain symmetry, leverage time domain symmetry, and like geometry symmetry of the material. Like this is isotopic material. It didn't matter which way you excite it. So that's really nice. So very good catch there. Yeah, congratulations.
Yeah.
There's another question in the chat. Emmanuel is asking how many points of edge loop predicted?
How many values?
How many steps of the edge loop? Did you downsample the 1024
we
to
used
a different number?
We used the full 1024 samples. Only when we were working with those 10 materials, there were a lot more samples available, right? There we would downsample a little bit, like every 8th sample we would use, because training would take way too long else. But for the 5 new materials, we used the full range of 1024 samples, since there were fewer samples to work with. So we had a full training on those new materials, have that finished in about 2 days, I would say, on a GPU.
Oh, one more question. You sort of didn't mention, did you do transfer learning? Looks like you are training every material from scratch. Is that true?
Yeah, we are training from scratch. There is no transfer learning in here.
Okay, that's very impressive. Like getting this result with training everything from scratch means that if I have a material and I don't have any other data, that's all I have, and this method may still work, while other transfer learning methods may rely on previous pre-training.
Right. Yeah. That was our reasoning behind that normalization with unifying the BH curves. I think that was also the reason why we could estimate the D data set, although there was a waveform missing, because through the unification of those BH curves, it's probably not so important that all waveforms are in the training set.
Right. One thing that I think it's valuable when you are doing a normalization, what we recently find after we are running this MagNet challenge, we have a paper coming from APAC, is we're normalizing to the B set, saturation flux density of the material. So because if you normalize to the existing data set, it really depends on how much you spend across the material behavior. But if you normalize to the like a physical limit of the material, that may give you a more better generality. So in the future, you guys may want to consider that direction.
Thanks. I would also like to mention here that it looks like a big construct here, but in each layer there are like 4 to 16 neurons or so, not more. If you use more neurons than 16, then everything gets too big very quick.
That's right. Yeah, it's very impressive that you are keeping 1024 units and still have a very small database. So that means every neuron is made well used. You're not wasting many parameters.
Yeah.
Yeah, great. Yeah, nice. Yeah, any other question from the audience? Okay, now let's move on to the third team. So, Tsinghua University.
Okay, thank you, Professor Chen.